Welcome to the Data Structures course. Today's topic is performance analysis and measurement. So what do you mean by performance analysis and how do we measure running time complexity of an algorithm? So we have already seen frequency count method in order to solve running time complexity of any given algorithm. So frequency count is nothing but the number of times a particular statement is executing. Okay, so that is our frequency count in which we associate cost to each statement. So now, what do you mean by performance analysis and how do we analyze algorithms in terms of time and space complexity? So in that, we will see different cases to analyze the performance of different algorithms that we will use to solve a particular problem. Okay, so let us see what is time and space complexity, or you can say asymptotic analysis. Okay, so asymptotic analysis is computing the running time in mathematical units. Okay, so we will compute the running time complexity and we will use mathematical notations for describing or expressing that time and space complexity. Okay, so in order to analyze the performance, we have to use three analysis cases, that is best case, average case and worst case analysis of an algorithm. Okay, that will help to conclude the performance of an algorithm. Okay, so if we are having a problem statement and for that we have more than one algorithm that will solve that problem, then we will analyze these two algorithms in terms of best case, average case and worst case. And this is how we can measure the performance of given algorithm. Okay, so time complexity can be expressed using asymptotic notations. Space complexity can also be expressed using asymptotic notations. So usually the time required by an algorithm falls under three cases, that is best case, average case and worst case. So best case describes the minimum time that is required for program execution. Average case means on an average how much time is required for program execution. And worst case is maximum time that is required for program execution. So in order to analyze the algorithm, we have to find best, average as well as worst case of an algorithm, and then we can describe all these cases using asymptotic notations. So what are asymptotic notations? These notations are mathematical notations which are used to express the running time complexity of an algorithm in a simple way by ignoring the constant and lower order terms from the time complexity. If we calculate frequency count of given algorithm, then we can use asymptotic notation to describe that frequency count in a simpler way. Okay, that ignores the constants and lower order terms from the frequency count. Okay, so that simplifies the expression of giving time and space complexity. So we have three notations: big O notation, big omega notation and big theta notation. So big O notation gives tight upper bound, big omega notation gives tight lower bound and big theta notation gives tight bound to the algorithm. So we will see what is tight upper bound, tight lower bound and tight bound of an algorithm. So before that, let us see classes of an algorithm, that how much time an algorithm can take and that falls under which class. So now let us compare all these classes of algorithms. So if any algorithm takes constant time, then its least time, or we can say best time we can get to run any algorithm. Okay, so time complexity will be what? Much more efficient. Logarithmic will take little more time than constant time. Okay, so as we move at right side, we will have worst time complexity. Okay, so factorial will take highest amount of time in order to execute. Fine. So this table indicates the complexity in terms of n, that is number of inputs. As number of input increases, the complexity increases. Okay, so for example, let's say this last cell, it is when number of input is 64 and we have exponential time, then it will take this much amount of time. Okay, so let's see this time complexity in relation with input. So as input size grows, time complexity grows. So the best time we can see in the graph that takes is order of 1, that is constant time. Okay, then we have logarithmic time, then linear time, then linear logarithmic, that is n log n time, then this is quadratic time, cubic time, this is exponential time, this is factorial time. So the highest time an algorithm takes is the factorial in this case. Okay, so this is how the classes of algorithm helps us to compare two algorithms. So now let us move to the asymptotic analysis. Okay, now let's see best case analysis. So what is best case running time? Best case running time is used to analyze an algorithm under optimal conditions. Means what can be the best situation when algorithm performs the best. For example, the best case for a simple linear search on an array occurs when the desired element is the first in the list. Okay, so say for example, if we want to find key element, that is 1. Okay, and if we linearly search this array, then we will compare this key element with elements in array one by one. Okay, so whenever we want to find key element, that is element 1 in this array, we have to compare key element 1 with this first element, and here match is found. Okay, so how much time it will take? It will take constant time. So if we want to search 1 in the array, it is present at the first position of the array. So it will take order of 1, means constant time to execute. So this can be the best case for linear search algorithm. When we want to find a key that is present at first position, then we will need only one comparison. So that will take constant amount of time, and that can be the best time, as we have seen in classes of algorithm. Average case analysis is the estimate of the running time for an average input. Means if we want to find a key in linear search that is in the middle of an array or around the middle index, then this can be considered as average case. So an average case running time assumes that all inputs of a given size are equally likely. Means we can get element to be searched that may be present at first index also. Element to be searched may be present at midway also, that is for example 11. The element which we are searching can be at middle index also. Okay, element which we want to search can be near to nth element also, that is if key is 32, then this is very near to nth element. So how do we find average case time? We will find all possible cases time and we will divide that by total number of cases. So for example, if we want to search the key which is present at first index, then it will take constant time, that is 1. If we want to find key that is 4, then it will take 2 comparisons. If you want to find key that is 7, then it will take 3 comparisons. Okay, so what we will do? We will find all likely inputs and then we will add up all this time. If we want to find key 12, so that is present at nth element. Okay, so it will take n number of comparisons. So what we will do? We will add up all the possible cases running time and we will divide it by total number of time, that is n. What will be the summation of 1 plus 2 up to n? It is a series that will be reduced to n into n plus 1 by 2. So the series will be reduced to n into n plus 1 by 2, and here we have total number of cases, that is n. So we will divide it by n. So this n and this n will be cancelled out and we will left with n plus 1 by 2. Okay, so in this case average case time complexity will be n plus 1 by 2. Now let us see worst case analysis. So worst case analysis denotes the behavior of an algorithm with respect to the worst possible case of the input instance. So in worst case analysis, we will think of the worst possible case while running or executing an algorithm in terms of some input. So the input element that is key to be found is 12. So 12 is present at the last index, that is nth index. Okay, so in order to find the given key, we have to traverse all the elements till the nth element. Okay, and we will find that element at the last index. So in that case, we have to traverse whole list, and that is the worst possible case in which we have to compare all the elements with the key. Okay, so this case is known as worst case analysis. If we talk about sorting, then for example, if we want to sort array in ascending order and we have input array which is in reverse order. Okay, for example, let's say we have 5 elements in an array, that is our input array. Now we want to sort this array in ascending order. Then this is the worst case for us, as our array is sorted in reverse order, but we want sorted array in ascending order. Okay, so in order to do this, we have to switch all the elements one by one, and it will take much amount of time. So this is also an example of worst case analysis of the given problem. So in the linear search, the worst case happens when the item we are searching is in the last position of the array, as we have already discussed. Now let us see big O notation. When we want to compare two algorithms in terms of f of n and g of n, then we can say that f of n is big O of g of n when some condition holds true. Okay, so in that case, for example, if we have found frequency count of an algorithm as 3n plus 5, then we can express this as order of g of n, that is n. Why is that so? Because n is the term which will affect the running time complexity of an algorithm more than this constant, because as n increases, our complexity will increase. Okay, so the term that will affect the algorithm's running time complexity is the term n. Okay, so in order to use asymptotic notation, what we will do, we will write this function f of n as order of n. So big O notation generally cares about the worst case scenario. If f of n and g of n are the functions defined on a positive integer number, that is n, which is our input size, then we can say that f of n is big O of g of n. So when we can say this, we can say this if there exists positive constant c and n0 such that this will hold true. This will hold true for all n greater than or equals to n0. So this is some initial value of n0. We will find this initial value, after which c into g of n will be always faster, or it will grow faster than f of n. Suppose we have found frequency count of an algorithm as 2n square plus n. Now if you want to express this in terms of g of n function, then this should be less than or equals to some constant time g of n. As shown in graph, g of n grows faster than f of n, means value of g of n should be greater than this f of n. So how do we find value of constant c and n0 such that this condition will always be true? Okay, so g of n is a faster function than f of n. So in g of n, we can choose g of n as c into n square also, but g of n is faster, so we can also write c into n cube. We can also write c into n raised to 4 and so on. Okay, but what we will choose? We will choose g of n as n square, as this gives tight upper bound. Okay, Big O notation gives tight upper bound to the algorithm. Means the closest value to f of n will be selected as g of n. Okay, now in order to prove this condition true, we need to find some constant c. So as we have seen here in f of n we have 2n square plus n. If we choose our constant c as 2, okay, then we will have 2n square, but f of n is 2n square plus n, so obviously this is greater function, but we want to prove that f of n grows slower than g of n. Then in that case we will select the constant term as 3. Okay, so if we take this constant as 3, then we can prove that 2n square plus n will always grow slower than 3n square. Now let us see big omega notation. So the omega notation provides the tight lower bound for f of n. So as we had seen in big O notation, here omega provides tight lower bound for f of n. What do you mean by tight lower bound? So if f of n is 2n square plus n, then lower bound of n square will be any value which belongs to the lower classes of quadratic class. Okay, so the classes which takes less time than n square is constant time, then log n time, then linear time, and so on. Okay, so these are the classes which take less time than n square time. So all of these functions can be g of n, but we will select g of n such that it will be closest to f of n, so that will be n square, as our f of n is n square. Fine. So this is how we can say that big omega provides tight lower bound for f of n. So we will choose g of n as n square. Fine. So it measures the best case time complexity, means the minimum amount of time an algorithm can take, or the best amount of time an algorithm possibly take to complete. So this is the graph of omega, in which we have function f of n which always grow faster than c into g of n. Means in this case we have to find g of n such that it will be always less than or equals to f of n. Fine. So we can say f of n is omega of g of n if there exists positive constant c and initial value n0, such that we will have c into g of n such that c into g of n will be less than or equals to f of n for all possible values of n which is greater than initial value n0. So in this case again we have to find some constant c and n0 such that your f of n will always grow faster than g of n. Okay, so in this case g of n is an asymptotically tight lower bound for f of n, means g of n will be less than f of n. Fine. So in this example, let's say if f of n is 2n square plus 2, then we have to select g of n such that f of n will always be greater than or equals to c into g of n. So in this case we can select any constant as c. So if we will select g of n as n square and c as 1, then this will always hold true. Okay, so in this case we can select our constant as 1. Let us now see big theta notation. So theta notation is simply written as f of n belongs to theta of g of n, where n is the problem size. Big theta notation gives exact bound for function f of n. So in this case, function f of n will grow between g of n with some constant c1. So it will be always grow faster than c1 into g of n, and will always grow slower than some constant c2 into g of n. So in this case, we have to find two constant. So in this case, we have to find two constants c1 and c2 such that this condition will hold true for any value of n which is greater than n0. So we will find some initial value n0 and two constants c1 and c2 such that this condition will always hold true for this. So for example, if f of n is 2n square plus n, then as we had seen in big O notation, we had selected this constant as 3 and g as n square. And as we had seen in omega, we had selected a constant as 1 and g of n as n square. So in this case, c1 will be 1 and c2 will be 3, and this will hold true for values 1 and 3. Means theta provides tight bound for f of n. Means f of n will always grow between these two values of g of n with constant c1 and c2.